Hey guys, this is a lecture video on section 5.1. We're going to talk about angles and how we measure them in two different measurement standards. So what I want to do first is I want to make sure we're very comfortable with angles in degrees. That's the first way we like to learn angles, and it's the way that's most familiar to most of us. So I'm going to start by drawing like a coordinate plane, so an XY axis. So we know when we're talking about the coordinate plane, we have the x-axis going horizontally and the y-axis going up and down. And when we talk about angles in the plane, which we will be talking about a lot, we like to talk about angles in standard position. So you're going to see that today in some of your homework problems. It's going to tell you to sketch an angle in standard position. Standard position is where the vertex of the angle is at the origin. Now an angle has two sides, an initial side and a terminal side. The initial side, where we start before we've done any rotation, in standard position the initial side is the positive x-axis. So we start at the origin and we come out to the right. So here's our initial side. And your terminal side is what determines the measure of your angle. So just as an example, this angle in standard position has a terminal side. Let's say it's going up like this. The angle isn't either side, right? The angle is the rotation that happened from initial to terminal. So when we measure this, guys, we do need to know which way we're rotating. So if you're in standard position, and notice I rotated counterclockwise to get up to this terminal side. Anytime you're rotating counterclockwise, your angle measure is going to be positive. But what if I had an angle and I started in standard position and I rotated down to get to my terminal side? So I'm going to erase this. It's in the way. You guys, what if I rotated clockwise and I rotated down this way? Well, if you rotate clockwise, your angle measure is going to be a negative value. So it's not really just about where your terminal side lands, it's about which way you took to get there. And it's really important to know. Okay, so we have counterclockwise positive, clockwise negative. Let's graph a couple of angles in degrees that we know for sure. So you guys, with your initial side here at the positive x-axis, if I rotated counterclockwise and I ended straight up the y-axis, so here's my terminal side, I rotated from here to here, I know that that's a 90-degree angle, right? So this here is a right angle. So I'm going to write 90 degrees up here because that terminal side ends straight up the y-axis. Starting from here, if I went all the way over to the other side of the x-axis and my terminal side ended here. So we went all the way over this way counterclockwise, half a full rotation. Then this is our 180 degrees. But starting at the initial side, if I went 3/4 of the way around counterclockwise, I would be down here at positive 270 degrees. And then guys, if you go an entire rotation all the way around, landing back to where you started, we went in one full clockwise rotation, we would be back at the x-axis, and that full rotation would be 360 degrees. So these are things you probably already know, but I just want to refresh. All right, so that outlines some of our positive angles. I'm going to erase a little bit off of this circle so I have some room, and we'll talk about some negative angles. I'm going to leave those positive angle values up that we found. to see how they compare with the negatives. All right, so here we are at our initial side. It's still going to be in standard position, which means our initial side is this positive x-axis. And this time I'm going to rotate counterclockwise to get to a couple of values. So if I rotate counterclockwise and end here with the straight down negative y-axis area, this, while it is 270, if I was going the other way, it would be negative 90 in a negative direction. So you guys, 270 and negative 90 are actually the same angle. Well, their terminal side ends at the same place. They're not the same angle because the direction to get there was different. So if we go down to negative 90, if you keep going this way and end here, you guys, we've gone negative 180. So 180 and negative 180 have that same terminal side, but they are not the same exact angle because of the rotation difference. And then guys, go all the way here. So this is a negative 3/4 rotation. This 90 that's positive is also a negative 270. And then once we go all the way back around in a clockwise rotation back to where we started, we could call this negative 360, as well as positive 360 going the other direction. So that's how it works with the positive and negative, and we've noted some important angles in degrees. Now, like I said, degree measure is what we're used to. It's very common when people talk about angles, they often talk about angles in degrees. But for a lot of applications, angles in degree measure are not very convenient. So in this class, we're going to do some of those applications. So I do want to look at a different angle measure, and it's called radians. So instead of using degrees, I'm going to use radians. Okay, so how do you find radians? I'm going to start by drawing a circle. It's very circular based measurement. So let's say we have a circle. Let's pretend it's a perfect circle. I'm not the best artist. Let's draw a line going from the center of the circle out to a point on the circle. You guys, what is this length when you have a circle? It's the radius, right? From the center out to the edge. So I'm going to label this with an R. That's the radius of this circle. Now, let's give it a terminal side here. I'm not going to label it differently because it's the terminal as opposed to the initial, because guys, I want you to note, and I don't want you to get confused, the length of the terminal side is also R. Yes, there's an initial and a terminal, but since I have the length R here, I want to put the length R there. So both of these have a length of R. This in the middle, I'm going to call the angle we've created theta. Notice I did go counterclockwise, so this is going to be a positive angle measure. You guys, theta, when it comes off of the center of the circle this way, we like to call this kind of theta a central angle. So you're going to see the word central angle in your homework, and I want to make sure you know what that means. It means you've got a circle and the two sides come out from the center and create this central angle. So we have theta as the central angle created by these two sides that are both length R. And then the last thing we need is to talk about this little piece of the outside of this circle. You guys, the whole way around the circle is the circumference, right? Well, my angle has intercepted part of this circumference, and I need to know the length of this to help me find the radian measure of the angle. So you guys, this little length that our angle creates, or it intercepts or cuts off of the rest of the circle, we call that S, or arc length. So we have a central angle theta. we have the radius of the circle r, and we have the arc length that our angle has created called s. Once you have all three of these things, we can talk about how to find theta, the central angle, and I'm going to put a capital R down here to note that this theta is in radians. I'm not always going to write that, but today especially we're going to be looking at degree measure and radian measure. I want us to be able to tell the difference. So to find theta in radians, it's a real simple formula using these variables. It's just S over R. So it's arc length over the radius of the circle. If you have this ratio, you can calculate it to find the radian measure of any angle. So radian measure is just arc length over radius all the time. One thing I want to note, as you're working homework problems, and we'll do some examples here in a minute, for this to work, S and R have to be the same unit. So for example, you're working a problem, if they give you S in feet and R in inches, you would have to make both S and R the same unit. So you might make them both inches, or you might make them both feet, depending on what you have. But they have to be in the same units to get an accurate radian measure. So let's do an example. I'm going to leave our S over R and our little note. All right, so I want to find the radian measure for an angle that is on a circle. So on a circle of radius 4 meters, find the radian measure of a central angle theta that intercepts an arc of length 1 meter. Okay, so in these problems, they're going to say things like central angle and intercepts an arc and circle of radius, whatever. Those are the keywords you're looking for. Remember, you just need these three things. One of them is what you're not going to know, right? But you can find the other. So in this case, we're looking for theta in radians. It's got to give you both S and R. So all you got to do is find them. Radius is 4 meters. So R is 4 meters. Where's S? Well, it doesn't just say S equals, right? Remember, it's the arc length. So an arc of length, there's your S, 1 meter. They're both in meters, so I don't have to worry about converting any units here. They are in the same units, so I can put them right into the formula. So the central angle that we're looking for here in radians is going to be 1 meter over 4 meters. Radians is a unitless measure, so one reason why it's important to have these in the same units is so when you do the division, the units do cancel out and you just get a number. So it's not going to say meters anymore or anything like that. It's just going to be a number. So theta in radians, that's weird, is just going to be 1/4. So 1/4 of a radian basically is the radian measure of this angle. So it's pretty easy. You guys, this is an easy formula. We are going to use it quite a bit in this lecture. So you guys, it seems totally different from the way degrees work. But I want to show you the relationship between radians and degrees. Our goal is to be able to take an angle measured in degrees and convert it to radians, or vice versa. So take it from radians and find it in degree measure. So using what I know about the radian measure, the arc length, the radius, sorry, I am going to find out how to convert the two. Here's our angle in standard position, you guys. Let's start at the initial side. Let's go counterclockwise an entire rotation and come back where we started. In degrees, what is this measure? Well, I know it's 360. It's one full rotation. So let's put this on a circle so I can think of it in terms of radians. Again, pretend this is a good circle. Just humor me, right? Okay, so let's think about it in radians. Let's call the radius r. Now that I've created a circle, we can say this is the center. This is any edge point of the circle. So we've got our radius r. The angle we're looking for is this theta, the one that goes one full rotation. Let's think about the arc that's intercepted by this angle. You start with your initial side and you take it all the way around and it ends up back where it started. Our angle has intercepted an arc that is the total circumference of a circle. That's the goal, right? I want to know what is one full rotation in radians. Okay, so I know it's 360 degrees. Let's find it in radians. So what do we need for radians? We need S and R. This is going to be a formula derivation that works for all of our examples. So notice it doesn't have any exact values here. So theta in radians equals, let's find another way to say S. The arc length is the whole circumference of the circle, right? So instead of just writing S, why don't I write the circumference of a circle? Isn't that 2 pi r? Little geometry there for you. The entire circumference could be labeled as 2 pi r for any circle. So here's the arc length, and I'm going to leave r as r. And you guys, what happens here? I've got an r on top and an r on the bottom, so those can cancel out. And I actually get theta in radians for a full rotation of any circle is 2 pi. I knew it was 360 degrees. Now I know a full rotation in radians is 2 pi. Sorry. So, this is a good start on the relationship between degrees and radians. I know 360 degrees and 2 pi radians are equivalent as far as the angle that they're measuring. Okay, so that's a good start. Let's find some of our other familiar degrees and turn them into radians. So if an entire rotation is 360 and 2 pi, so if you start here, go all the way around, and that's 2 pi radians, or 360 degrees. Let's talk about 180. So if you start here and go half a rotation, well, I know it's 180 in degrees. You guys, it's easy to find out what it would be in radians without having to do that whole thing we just did again, right? So 360 to 180, I've cut that in half because I went from a full rotation to a half a rotation. So, sorry, allergies are super bad today. But anyway, guys, cut it in half. I'm going to cut the radian measure in half too. So if a full rotation is 2 pi, a half a rotation is 1 pi, or just pi. Let's cut it some more. Well, if a half a rotation is just pi, what about a quarter of a rotation? So 90 degrees, just take this one and cut it in half, right? So I'm going to get a half of pi, or we can call that pi over 2. That's how we write that. So you guys, these are some examples of familiar degree terms into radians. You're going to get really used to angle measures like pi and 2 pi and pi over 2, and we can even keep going and find other angles that we know in degrees, but now we're going to know them in radians. So you guys, this particular relationship where the pi is by itself, we're going to use this relationship between 180 degrees and pi radians. We're going to come up with a formula to convert any angle from degrees to radians or back the other direction. So because they measure the exact same thing, would you agree that the fraction pi over 180 degrees would equal 1? They are different units of measure, but they measure the exact same thing, guys. So they are technically equivalent on top and bottom. We are going to use this fact, and if pi over 180 degrees equals 1, I would say 180 degrees over pi also equals 1. So you guys, we have two fractions that are equal to 1. These are what's going to get us back and forth between degrees and radians, and I'll show you how. You guys, when we use pi, and you'll notice that our radian measures almost always have a pi in them, it's because of the circular nature of radians. So we start to correspond pi with radian measure. So I want you to keep that in mind as I do this conversion. So to find a measure in radians, starting with the measure in degrees. So I have some angle that's in degrees, but I want to put it into radians. I take that degrees, and I'm going to multiply by pi over 180. So let's think about why I'm doing this. I'm in degrees. I want it to be in radians, which means I want it to have a pi in it at the end. And I want to get the degrees out, so that's why I'm dividing by a degree measure. Why am I using pi over 180? Well, because it equals 1. It's not changing the angle measure, it's just changing the units it's in. So let's do an example. So I'm looking for theta in radians, and the degree I'm going to start with is 120 degrees. So I'm going to take 120 degrees, and I'm going to put it into radians. So if I take that 120 degrees, and I multiply by pi over 180, let's see what happens. Well, this 120, this degree measure is always on top, right? You could say it's 120 degrees over 1. So I have 120 degrees and a pi on the top. On the bottom, I just have 180 degrees. So here's what's happening. Notice the degree units cancel each other out, so I'm not in degrees anymore. And I have a pi in there. It seems like everything's going the way I wanted it to. So from here, I have 120 pi over 180. I'm just going to reduce this fraction as much as possible. So I can easily take 10 out of top and bottom and get 12 pi over 18, but I could go further than that. You guys, I could take 6 out of the top and bottom and get 2 pi over 3. And once I'm totally reduced, this is the radian measure of 120 degrees. These are the exact same angle, but I took the degrees and I put it into radians. You're going to have some questions just like this. It'll have you convert degrees to radians or maybe back the other way. But on one set of questions, it says to leave your answers in terms of pi. That's when you're going to see reduced fractions with a pi on the top. So like 2 pi over 3 is going to be your answer. You do have some questions that want you to round your answer. If it said to round, you would have to put 2 pi over 3 into your calculator and then get a rounded value. But on this one, leaving answers in terms of pi, I'm looking for 2 pi over 3. Let's do one where it wants me to round. All right, guys, so on this one, I have an angle of 55.4 degrees. but I want to put it in radians. So remember, you start with what you want to find on the one on the side alone. And so I want radian measure. So what I'm going to do is I'm going to take the degree measure and multiply it by pi over 180. I'm putting in a pi, I'm taking out degrees, like putting in radians, taking out degrees. That's how I know which fraction to use. So canceling out the degrees, putting the 55.4 on the top, I get 55.4 pi over 180. And on a question like this, in this section of your homework, it wants you to put it in your calculator and round to the nearest hundredth. So that's what I'm going to do. You guys, in this class, it's really important to know your way around your calculator. You know, where the pi button is, how to put things in and make sure it gets in the right order. So you kind of have to play around with it sometimes, but just make sure you can get the answers that I get when you watch the video. So I put in the 54 times pi, and I'm going to divide by 180. And my radian measure is 0.97, rounded to the nearest hundredth. So here's a rounded answer, here's an exact answer in terms of pi, and you'll be giving both depending on what section you're doing on your homework. So both of these went from radians to degrees. Let's do two problems, exact and then rounded, going from degrees to radians. All right, guys, that's what we just did. We went from degrees to radians. Now we're going to go from radians to degrees. Okay, so going from radians to degrees, we need a different version of this formula. So what I want, my result needs to be the degree measure. What I'm starting with is theta in radians. I'm going to multiply it by one of those fractions, but this time instead of pi over 180, I want to put the degrees in. So the 180 is going to go on top, and I want to take out the pi because I don't want radians anymore. So 180 over pi gets you radians, or sorry guys, I'm getting so confused. It gets you degrees. It puts the degrees in, it takes the radians out. So let's do an example. In this case, do as I do, not as I say. Okay, anyway, so I want the degree measure for 5 pi over 6 radians. So I have 5 pi over 6 radians. I'm going to multiply that by 180 degrees over pi. Notice our pi's are what's going to cancel out this time, and the degree unit is going to stay. So I cancel out those pi's. I get 5 times 180 degrees over 6. And you guys, that's where you just do the math. So you can stick it in your calculator and do 5 times 180 over 6. You could reduce it beforehand if you want to. Either way, it's a pretty quick calculation. And you should get 150 degrees. Make sure you do keep the degree unit in there because you wanted degrees, so you got degrees. This is what it's going to look like. On those questions where it wants an exact answer, you will get a nice exact value when you do that division. Sometimes our answers are not exact though. So let's look at one where we might have to round. So I want to take 1.4 radians and I want to convert it to degrees. So no matter what your measure looks like, you still use the same formula. Sometimes it's just messier than others. So to get degrees here, I take my radian measure, which is 1.4. Notice there's no pi in here. It's because my answer isn't in an exact version in terms of pi. That's okay. When I want degrees, I'm still going to take a pi out of the expression and put the degrees in. So it's still going to be 180 degrees over pi. So on this one, notice we don't have that nice pi cancellation. That's okay. We're just going to be throwing this in our calculator. So this 1.4, it is on top, you guys. It's like 1.4 over 1. So what we're going to do in our calculator is we're going to do 1.4 times 180, and then just divide it by pi. So let's do that. Divide by pi. And you guys, what I get on this one is 80.21 degrees. And again, it said round to the nearest hundredth, so that's what I did. So, an exact and a non-exact version of converting from radians to degrees. I think I got it right that time. Okay, moving on. So radian measure is so great in so many applications, and I already said that, but let's do some of them. The first thing we're going to do is we're going to work again with this formula. I know this gives me radian measure, I know this is arc length, and I know this is the radius of a circle. Well, sometimes we're going to just solve for theta like we did in an example before. Sometimes one of these might be your unknown. If you know two of these things, you can always find the other one. So let's look at a couple of examples of that. So in this problem, I have a circle of radius 4 meters. It tells me that there's a central angle called theta, and it gives me the actual measure of that angle. So it's giving me theta, which means that's not what I'm looking for in the problem. And it says theta is 41 degrees. Okay. What does it want? Well, it wants the only unknown in the problem. It gave me r and it gave me theta. I must be looking for s, and it does. It says, what's the arc length? This one says rounded, so it'll be a rounded problem. So let's think about this. R is going to be 4 meters. That's clear. Radius, radius. But you guys, I need to think a little bit on theta. What does this equation, S over R, give me? It gives me theta in radians, right? This formula only holds together when that angle is in radian measure. So here's a problem. The angle it gave me is in degrees. Well, what am I going to do before I can even start solving for S? I have to convert this to radians first. Anytime you're using this particular formula, theta only works in radians. A lot of times they do this to you. They try to trick you, make you do one extra step, get this in radians, and then solve the problem. Okay, so that's the first step. I have 41 degrees, but I need it in radians. So remember, to get radians, take your degree measure. I want to put a pi in, and I want to take 180 out. This is a calculator question. Like I said, it's not exact. It's a rounded problem. So I can put 41 pi over 180 into my calculator and get a value. Now, instead of going ahead and doing that in my calculator, do you think it would be better to take this, which is exact, right? I haven't rounded anything yet, and go ahead and use it to solve the equation to cut down on rounding error? I think it's a great idea. So let's do that. Anytime you can not round a value that's part of your solution, then don't round it, just wait. So you guys, let's wait. Let's just call this 41 pi over 180 and then continue with the problem. So our theta is 41 pi over 180. Remember, we're looking for S, but we do know the radius is 4. So we're here. I am trying to solve for S, so I need to multiply both sides by 4. That should get S by itself, right? So with S by itself, I have the 41 pi over 180 multiplied by 4. Remember, that's just 4 over 1, so this 4 is actually going on top. So Another way to write that is, why don't we do 41 times 4? That's 164, right? So it'd be 164 pi over 180. Now let's put it in our calculator because we're getting the final answer, and that does have to be rounded. So in my calculator, I'm going to do 164 times pi and then divide by 180. And I get my answer for S. I get 2.86. I think this one said nearest hundredth also. You just always make sure you know what it's looking for in the instructions. 2.86 what? Meters. Remember, S and R are the same units, or they have to be the same units for this equation to hold. So because I already knew the measure of theta and I already knew R, you know S is also going to be in meters. So 2.86 meters, and we found our arc length. All right, let me see what I got for you next. Okay, so we are going to move on to a different type of problem. I do want to note for you that a couple of these problems are having you solve for theta, which we did an example of. Some of them have you solve for R, so maybe it gives you theta and it gives you S. As long as you make sure theta is in radians for all of these cases, just solving for the unknown is basic algebra and putting in what you do know, isolating either R, S, or theta. So those shouldn't give you too much problems. If they do, you can always hit me up in the office hours on Zoom. So let's move on. You guys, so we know how to find arc length. We know how to solve for anything in here. While we're on the subject of central angles and radius and arcs, let's say I'm on a circle, I've got the arc length of R. Let's say the terminal side is here. Remember, this length is also R. Here's your arc length, S. What if I want to know the whole area, not just how long this little piece that intersects on the circle is, but what if I want to know the entire area of this, what we call sector of the circle? So what sector is our angle theta cutting out of this circle? You guys, to find the area, so this, what I'm looking for is called a sector, this little piece right here, however big or small it may be, depending on your angle. I want to find the area of that sector. So to find the area of a sector, we have a formula. So you guys, the area is going to be 1/2 times theta times the radius squared. So this is something you want to remember. What do you think the measure of theta is going to be in? Yeah, it's going to be in radians. You guys, theta has to be in radians, just like this example here. So anytime you're looking for arc length or area of a sector, theta has to be in radians. That's the theta that this all works with. Theta in degrees has nothing to do with this. So, as long as theta is in radians, this should be a piece of cake. And I want to note that here, theta has to be in radians. And then we're going to do an example. So, example. I'm going to leave that. So let's say we have a circle where the radius is 1.5 centimeters. I also know that theta is 7 pi over 6. And I want to know the area of the sector. So for the area of the sector, I need R, I need the radius, and I need theta. 1/2 is 1/2 all day long. So I just need theta and R. I need to make sure theta is in radians. So do I have this information now? I have theta. How can you tell if this is in radians or not? Well, One big clue is that it's in terms of pi. There's a pi in there. More than likely it's in radians. The other way you can tell, it doesn't have a degree symbol. If it doesn't have a degree symbol, it has to be radians. So we are already in radians. My radius is right here. It says r is 1.5. I think I can just plug it all into the formula, and that's what I'm going to do. So the area here is 1/2 times theta, so 7 pi over 6, times r squared. Make sure the only thing you square is r. This doesn't get squared. Make sure you don't multiply these together and then square. You guys, order of operations. You square this one thing, then you can continue with the multiplication. So you guys, I can't actually remember if this question is exact or a rounding question. So I'm going to do it exact and then round it so we have both. So we have the 1/2 times the 7 pi over 6. Let's go ahead and round square 1.5. So you guys, 1.5 squared is 2.25. So I need to multiply all this together. The more I look at it, the more I think this is probably a rounding question, but I'm still going to work it exact and then round. So let's bring it up here. So 1/2 times 7 pi over 6. Remember, when you're rounding a fraction, it's just straight across the top, straight across the bottom. So 1 times 7 pi is 7 pi. 2 times 6 is 12. And I still have that 2.25 that I have to multiply. So let's go ahead and put that in there. So I do need a calculator for that. You guys, I'm never, and you'll notice I'm never super confident in my basic arithmetic skills because I always make a silly mistake. So I do rely on the security of my calculator, even on easy stuff. You guys, that's 7 times 2.25 is 15.75. Notice I'm leaving the pi as pi. So I have 15.75 pi over 12. Technically, this would be in terms of pi. I really think this is a rounded question, so let's go ahead and put it in and round it. So I'm going to do 15.75 times pi and then divide by 12. What I get is 4.12 if it's rounded to the nearest hundredth. You guys, how do I know what units I'm in? Well, it's going to be the same units as the radius, but because it's an area, it's going to be centimeters squared, right? So centimeters squared or square centimeters, however you want to write it in there. I'm sure Alex has a way that it makes you do it. Okay, so that's an area question. You guys, the last thing I want to do, now that we know both degrees and radians, I want to do some examples where we sketch different angles in the plane, so the coordinate plane. And some of them are going to be degrees and some of them are going to be radians. Some will be positive, some will be negative. We're just going to do an assortment. So these are all going to be sketch questions, and you will have questions like this on your homework. Obviously, you're not literally going to sketch it, but you'll fill in a graph where the angle would be. So let's start with a degree. Let's sketch theta equals 60 degrees. We'll start kind of easy. So 60 degrees. Let's think about our landmark angles for degrees. We would start at 0. If it was all the way around, I know it would be 360. We have the 90 up here, the 180, and the 270. So you guys, 60 degrees, where's it going to fall? It's going to fall somewhere between 0 and 90, right? It's more than halfway. So you guys, this would be the halfway point between 0 and 90. That'd be like 45, right? So it's going to be a little more than that. So I would sketch an angle right here. I think Alex makes it pretty simple to graph these. I think it gives little marks like this, where would 30 and 45 and 60 be? And you'll see when you get there. But since I am just sketching, and I'm not sketching on a very pretty exact Alex graph, I'm sketching it about right there, about 60 degrees. So, done. On this same graph, I want to sketch theta equals negative 210 degrees. So let's go clockwise, right? I have to remember which way is negative. I can't just say, oh, 210, it's bigger than 180, so it's over here somewhere. Not necessarily if I'm going negative, right? So, going negative, let's erase our positive landmarks. So this is 0, going negative, this is negative 90, right? And negative 180, and negative 270 is up here. And this, we could call that negative 360. So going negative 210 degrees. It's bigger than, well, technically smaller than negative 90. I go further than 90. I go further than 180, you guys, but I don't go all the way up to 270. You guys, what's the difference between negative 180 and negative 210? It's just 30 degrees, right? So I hit 180 and I go about 30 degrees more. And here is negative 210. It lands right here. So you guys, these are probably going to be pretty easy for you. You'll see how they work really quickly. Of course, me drawing them out without a nice, pretty graph to draw on, it's kind of iffy, but it's going to be easier for you and Alex. So let's do, actually, I'm still in degrees. I want to clean up my graph a little bit. What if it throws you for a loop and it wants you to sketch theta equals 600? Sorry. And you say, what? 600? I only go up to 360, right? 90, 180, 270, 360. How do I graph 600? Well, you guys, angles are circular. You can just keep going around and around. It's not about where it lands, remember? It's about how it got there. So let's think about 600. Starting in standard position where initial side is here on the positive x-axis. If we go all the way around once, we're at 360. But I need more than that. How much more than that? I'm going to calculate it. Let's take a rotation off and see what's left over. So if you have an angle that's larger than one full rotation, I need to find its corresponding angle that is on one full rotation. So I do some subtraction and I get what? 240? So I've already gone 360. I need to go 240 more. So here's 90 more. What would that be? Okay, I'm going to go all the way around. So it's past 90, it's past 180, but it's not quite to 270. Remember, this would be going 270. So I'm going to leave it about here. So this is what my angle looks like. This is 600 degrees. But also, if I took off one of those rotations, like I did here, if I minused 360 and just went around starting from here, straight to here, what would this angle also be? Well, it would also be 240. So you guys, it looks like all I have to do is when I have an angle that's larger than 360 and I want to graph it, or I just want to know what it would be on one rotation, just take a rotation off. You guys, so I took off 360, I was left with 240. This is 240. It's also 600. You guys, this is what we call a pair of coterminal angles. While their measure is not the same, their terminal side is exactly the same. So I want you to note that what we found here between 600 and 240 is a relationship we call coterminal angles. You're going to have to find some. How did we find it? When we have a large angle, we subtracted 360 and we got the angle that was within one full rotation. We always want to be between 0 and 360 so we can sketch, so we can work with that angle. So they might give you an angle like 600. They might say, what's a coterminal angle on one rotation? Subtract 360, get here to the 240. What if they gave you an angle, again, looking for coterminal, but this time the angle they give you is negative. Let's say we start with negative 120. All right, so I want to sketch negative, well, I don't want to sketch it, I want to find coterminal, sorry. I guess we can sketch it also. Negative 120, this is pretty easy to sketch actually. Starting on the initial side, remember this is negative 90, if we're going in the negative direction, this is negative 180, so it's between the two. You guys, would it be closer to the 90 or the 180? Well, it's 30 degrees away from 120, 90 is, and 180 is 60 degrees away, so it's going to be about right here, about 30 more than the negative 90. So I'm going to sketch that. This angle looks familiar from the last question, but we're going to find out why. So I'm here at negative 120. So, okay, we got it. We can sketch it. What if I want to find a coterminal angle to negative 120? Really? Sorry, I struggled with that one. Coterminal to negative 180 within one positive rotation. You guys, you'll notice that when we're looking for coterminal angles, it's not enough to just say I want it within one rotation. You're always going to find it within one positive rotation. So I say, oh, 120, it's within one rotation, but it's a negative. You guys, that's the problem. I need to make it positive. So how do you think I can go from a negative 120 to a positive angle that ends in the same place? What if I'm here at negative 120 and I just add a full rotation? What's going to happen? Well, I take care of my negative part and then I start going around to a positive angle, right? So if you've got a negative value and you want a coterminal angle, add a rotation. So if my angle was large, I subtracted a rotation and I got there. If my angle is really small, like negative, I'm going to add a rotation and get to where I want to be. So let's add 360 this time. What happens? Negative 120 plus 360, I get 240. That's why it looks familiar, because this negative 120 is also coterminal with positive 240. So you guys, I have this 240. Coterminal with negative 120. What else was it coterminal with? It was positive 600, right? I could just add another rotation and find another one. I could keep adding rotations or keep subtracting rotations, and I can find an infinite number of angles that are coterminal with this one. You guys, every single angle on your graph has an infinite number of coterminal angles because you can go around and rotate over and over and over and just keep adding to your angle measure. But the point is, they're all going to stop somewhere on this graph where you've already had angles stop before. So, coterminal angles, there's tons of them. It's going to specify what it wants, and then you either add or subtract 360 to find it. All right, the last thing I want to do is I want to do a little bit of what we just did in degrees in radians. I try to keep these videos about the length of a lecture. I think we're a little bit over 50 minutes here, but the geometry review was pretty short. I try to limit it to about an hour, so I think we're about on track here. So we're going to sketch again, but this time in radians. So let's sketch theta equals pi over 4. So we have to think about radian measure now. So let's look at our landmark angles. Here's 0. You guys, degrees, radians, 0 is 0. If you don't rotate at all, you are at 0. What was straight up? What was the 90-degree radian equivalent? It was pi over 2, if you don't remember. Straight out at 180, that was pi. We didn't really talk about 270, but you would find out that the radian equivalent of 270 is 3 pi over 2. And then a full rotation is 2 pi. So we're going to keep these in mind as we sketch pi over 4. So you look at your angle. Where it needs to land is between two of your landmark angles, right? So I have pi over 4. Where is that? That's saying 1/4 of pi. Here's 0. Here's 1/2 of pi. It's going to be somewhere in here, right? I think it's going to be exactly halfway. Pi over 2, cut it in half. What do you get? You get pi over 4. So take your 90 degrees, or your pi over 2, cut it in half, and you have your angle pi over 4. It would be right in the middle of these two. So AKA 45 degrees, if you want to know another relationship between degrees and radians. Here's a pair for you, pi over 4, 45 degrees. They're the same angle. But we are working in radians right now. Let's do another one. Let's do a negative. Let's do theta equals negative 11 pi over 6. So you guys, this one seems kind of crazy and complicated. 11 pi over 6 is an angle we use a lot, so putting a negative on it is not going to be that crazy. Right now it is, sure, because radians is new to us, but you'll get used to all the special radian angles that we use, and then it won't seem so crazy. But this one is negative, so let's think about 11 pi over 6 and where it lands on our circle. Let's change these to negative landmarks for us, just to help us out. So the pi, since we're going negative, is just going to be negative pi. This was pi over 2, but remember this is where the 270 goes now. So negative 3 pi over 2, negative pi over 2 would be down here, like negative 90, negative 180, negative 270. I just wrote them in radians. All the way around in clockwise would be negative 2 pi. So think about, you have to really be on it with fractions when we're talking about radians. I want to think about 11 pi over 6 and see which of these values it lies between. Let me erase this. Okay, 11 pi over 6. How does that relate to 2 pi? If I was at 12 pi over 6, wouldn't I be at 2 pi? So you guys, think about the denominator. Think about how many you have on top. 11 over 6, that's almost 2. So I think 11 pi over 6 is almost 2 pi, which means it's going to lie, because we're going negative, it's going to be all the way somewhere between here and here. It's bigger than 3 pi over 2. It's bigger than 3/2 pi, but it's not as big as 2 pi. So 11 pi over 6 going negative. It's bigger than 1 pi. It's bigger than 3/2 pi. It is so close. It's only 1 pi over 6 less than 2 pi, right? So it's probably about right here, really close. And that would be 11 pi over 6 negative. Again, guys, you'll get used to these. The radian measure, the fractions, we work with them so much. But this sketching is really helpful for you to practice. So you guys, one thing that's a little bit harder in radians than it is degrees is the concept of coterminal angles. But we're going to do 2, and that'll be the last thing we do. I know I'm hitting an hour here. Remember, when we're looking for coterminal angles, I want it within 1 positive rotation. That is always our goal. So in degrees, that was between 0 and 360. But in radians, that's between 0 and 2 pi, right? So I need to be between 0 and 2 pi. So let's draw one rotation here. This is 0 to 2 pi. Let's do theta equals, let me think for a minute, 5 pi over, no, that's actually between one rotation. 10 pi over 4. All right, how do I know that this is bigger than one rotation to begin with? Well, because guys, 10 over 4, is that bigger than 2? Because if it is, this is bigger than 2 pi, right? So 10 over 4 is bigger than 2 pi because 8 over 4 would be 2. This is larger. You have to be able to tell if it's bigger than one rotation or smaller than one rotation, and that's all about fractions, guys. So 10 pi over 4, another way you could write that would be 5 pi over 2, if you want to reduce, if that helps you. But either way, this is larger than 2 pi. Remember when we were looking at the degrees and we had that 600, it was bigger than one rotation. So what I did was I subtracted a full rotation. I subtracted 360. I can do the same exact thing here. It's just I'm not using the number 360 anymore. I'm using 2 pi because we're in radians. So coterminal, whether you're in radians or degrees, you're adding a rotation or you're subtracting a rotation. Here, because it's larger than 2 pi, it's larger than one full rotation, I'm going to subtract a full rotation, and what's left over is going to be the coterminal angle I'm looking for. So I need to take this and subtract, and I don't care which one you use. You can reduce it first if you want. Your question might not even be the same question, but anyway, I want to subtract 2 pi. So guys, when we're working with fractions, if I want to subtract or add, don't I have to get a common denominator? Well, yeah, this is 2 pi over 1. This case, if I'm using the reduced version, is 5 pi over 2. So I'm going to keep the 5 pi over 2, but I need to write 2 pi in terms of 2 in the denominator. So how can I rewrite 2 pi as something over 2? Well, wouldn't that be 4 pi over 2? I think so, you guys. So instead of writing 2 pi, I wrote 4 pi over 2. That was just to get a common denominator so I can do the subtraction. I'm taking away a full rotation. Notice that I'm still taking away 2 pi, I've just rewritten it. When you're subtracting fractions with common denominators, remember the denominator stays the same. You subtract what's on top. So I have 5 pi minus 4 pi. That leaves us with 1 pi over 2. Pi over 2, that's familiar, right? It should be getting familiar. That's at 90. So you guys, that 5 pi over 2 or 10 pi over 4, it's coterminal with 90 degrees. It's coterminal with pi over 2. Let's see how we got there. Here's normal pi over 2. We just went straight up 90 degrees. Let's talk about the 5 pi over 2. So here's 1 pi over 2, here's 2, here's 3, here's 4. Oh, there's 5. It is. They're coterminal. So pi over 2 and 5 pi over 2 are coterminal angles. So coterminal, add a rotation or subtract a rotation. If it's degrees, you add or subtract 360. If it's radians, you add or subtract 2 pi. All right, so I think that covers everything for 5.1. Sorry this video was a little long. It's a pretty large section, but that's all I got for you. So stay tuned for 5.2.